Good day, grade 12 students. Welcome to Bambo Telescuela. This is your school on air in Earth and Life Science. I am your teacher, Jaiseline Cornejo. Make sure to have your modules with you and tune into DWND-FM and CMD Cable Channel 1 and also streaming live at SDO Kawayan Facebook page. We have a lot of things to learn about. Come, join me as we start our week with fun and exciting adventure in Earth and Life Science. As we start, I want to show you some pictures. What can you say about these pictures? What similarities can you observe among them? You're right. All of them shows aftermaths of an earthquake. These are aftermaths of an earthquake in the Philippines. As you can see, roads, buildings, and churches tend to be destroyed whenever we have earthquakes that have a magnitude of higher than 5. Rocks that are deposited in horizontal layers are deformed by tectonic forces. These stresses are responsible for triggering earthquakes and contributing to other geological events such as landslides. At the boundaries of tectonic plates are the areas where the highest hazards are. This is where the plates have the highest tension and therefore are exit points for energy release. Our very own country, the Philippines, if you look at our location on our maps, you will notice that the country lies on the boundaries of the Philippine plate. What does this mean? Being near or at the boundary of the Philippine plate makes us prone to geohazards, especially when energy from the interior of Earth exits through these boundaries. This is caused by the Earth's plates converging, diverging, or transverging against one another. This causes the crust of the Earth to buckle and strain, generating incredible amounts of pressure that builds up as time progresses and may conclude in the release of energy. With those in mind, these 3 will be our goals for this week. Number 1, explain how the movement of plates lead to the formation of folds and folds. Number 2, describe how layers of rocks called stratified rocks are formed. And number 3, describe the different methods, relative and absolute dating to determine the age of rocks. Let's now dive into our first topic, folds and folds. How are they created? Folding is a type of movement resulting from the compression of rock layers. Bending, curving, crumpling, or buckling of rocks into folds is usually visible on rock strata. It is caused due to horizontal movements. Folding forces move toward a center. They are generally common in sedimentary rocks. It leads to the formation of mountains like Himalayan mountains and the Alps. It also occurs in seas and oceans. There are actually 3 types of folds. Number 1, we have the monocline. This is a simple bend in the rock layers so that they are no longer horizontal. Here is an illustration of what a monocline looks like. Number 2, anticline. These are folded rocks that are arched upward and dip away from the center of the fold. The oldest rocks are at the center of the anticline and the youngest are draped over them. When rocks arch upward and to form a circular structure, it is called a dome. Here is an illustration of an anticline. Number 3, a syncline. This is a fold that bends downward, causing the youngest rocks are to be at the center and the oldest are on outside. When rocks bend downward in a circular structure, it is called a basin. Here is an illustration of a syncline. Now look at these pictures. These are some examples of folded rocks: a monocline, an anticline, and a syncline. Before we proceed with faulting, let us recall the meaning of a hanging wall and a footwall. The hanging wall occurs above the fault line, and the footwall occurs below it. This terminology comes from mining. When working on a tabular ore body, the miner stood with the footwall under his feet and with the hanging wall above him. Faulting. This is a type of movement that forms cracks or fractures in rocks. These cracks are called fault lines. It is caused due to vertical movement. Forces move away from the common center. They are generally common in igneous and metamorphic rocks. It leads to the formation of sharp-peaked mountains and rift valleys. We actually have 3 types of faults. The first one is the normal fault. It forms when the hanging wall drops down. The forces that create normal fault are pulling the sides apart or extensional. Here is an illustration of how a normal fault would look like. Number 2, a reverse fault. From when the hanging wall moves up. The forces creating it are compressional, pushing the sides together. Here is an illustration of how a reverse fault looks like. Number 3, transcurrent or strike-slip fault. They have walls that move sideways, not up and down. Here is an illustration of a transcurrent or strike-slip fault. Now look at these pictures. These are some examples of a fault: a normal fault, a reverse fault, and a transcurrent or strike-slip fault. But how does that fault form? If a large slab or plate of Earth's surface is generally squeezed, the solid rock slowly wrinkles and crumples. Its layers become wavy folds. When in other places, rocks are stretched or bent, they crack or split along weak points. These cracks are known as faults. These 2 types of deformation, namely folding and faulting, that are strong enough to move ocean sediments to an elevation many thousands meters above sea level. Just a quick recap before we go to our next topic. Remember that folding and faulting are both caused by the movement of our plate tectonics. Number 2, folding results from the compression of rock layers which moves towards the center, while faulting forms cracks or fractures in rocks and move away from the center. Number 3, folding is caused by horizontal movements, while faulting is caused by vertical movement. Number 4, folding is generally common in sedimentary rocks, while faulting is in igneous and metamorphic rocks. And number 5, folding creates mountains, while faulting creates mountains and rift valleys. Ultimately, it is these stresses that sculpt the face of the Earth, creating new landforms and rest-lying the outlines of our continents. Let us now dive into our second topic for this week. How do stratified rocks form? But before that, let us define what is a stratified rock. Stratified rocks are layered earth materials deposited as successive beds of sediment and solidified by compaction, cementation, or crystallization, same as sedimentary rock. Although not all sedimentary rocks show visible stratification. In general, those rocks which are formed by deposition, compaction, and consolidation of sediments and has developed layers of strata in them is known as stratified rocks. What causes stratification?
Existing rocks can be broken down into small pieces or sediments in a process called weathering. There are three main types of weathering. Physical weathering is caused by temperature changes. For example, in freeze-thaw weathering, water gets into cracks in the rock. When the water freezes, it expands and forces the rock apart. This happens many times, eventually breaking the rock. An example of chemical weathering is when acid rain reacts with substances in rocks. Even plants or animals can break up rocks. This is biological weathering. The sediments formed by weathering can be moved away by water, ice, wind, or gravity. The combined process of weathering and transport is called erosion. Eventually, sediments settle in one place. For example, they may sink to the bottom of the sea. This is called deposition. More layers of sediment are deposited on top. Over millions of years, the weight of the layers above compress the ones below, and they harden into sedimentary rock in a process called compaction. Sometimes another substance seeps between the sediments and hardens, sticking or cementing the sediments together. The whole process leads to the formation of horizontal layers of sedimentary rock. So, erosion breaks old rocks into small pieces and transports the sediments. These are deposited in layers and compacted into sedimentary rocks. This explains the stripy appearance of the cliffs at the beach. Each stripe is a layer of sedimentary rock.
Stratification occurs as a result of density differential between two water layers and can arise as a result of the differences in salinity, temperature, or a combination of both. Stratification is more likely when the mixing of forces of wind and wave action are minimal, and this occurs more often in the summer months. The most common cause of stratification is variation in transporting ability of the depositing agent. Water and wind sort sediments according to size, weight, and shape of particles, and these sediments settle in layers of relative homogeneity. Differences in sediment composition resulting from different sources and variation in sediment brought about by changes in agents of deposition also lead to stratification. Stratification or layering not only occurs in most sedimentary rocks, but also in those igneous rocks formed at the Earth's surface, as from lava flows and volcanic fragmental deposits. The strata or layers range from several millimeters to many meters in thickness and vary greatly in shape. Stratification in volcanic rocks, in some respects from that in sedimentary rocks. Fragmental volcanic material becomes sorted in flight under the influence of gravity, particle size, and wind. Falling to the ground, it may form well-sorted layers. If it falls into lakes or seas, it becomes layered like any other waterborne detrital matter. Stratification also may result from successive flows of liquid lava or alternations between flows and ash falls. Here is a picture of what a volcanic stratified rock looks like. Not all sedimentary deposits are stratified. Those transported by ice alone, landslide deposits, and residual soils, for example, exhibit no stratification. Original stratification may be destroyed by plants and animals, by recrystallization of limestones, or by other disturbances subsequent to deposition. Strata may range from thin sheets that cover many square kilometers to thick lands like bodies that extend only a few meters laterally. For the next topic, we are going to see on how the stratified rocks are dated. Let's go! The age of stratified rocks intrigues almost everyone, including me. Almost everyone wants to know how old is a stratified rock. But they want to know, I also want to know, how that age was determined. As we proceed with how to date rocks. Geologists often need to know the age of material that they find. There are actually two different methods of determining the age of stratified rocks. We have absolute dating and relative dating methods, which have been used to establish the chronologies of rock art. Geologists use absolute dating methods, sometimes called numerical dating, to give rocks an actual date or date range in number of years. This is different from relative dating, which only puts geological events in time order. Let us dig deeper on how absolute dating works. To determine the absolute ages of fossils and rocks, scientists analyze the isotopes of radioactive elements. So what are isotopes? Isotopes are atoms of the same element that have the same number of protons, but different number of neutrons. Most isotopes are stable, meaning that they stay in their original form. Radioactive isotopes tend to break down into stable isotopes of the same or other element. The unstable radioactive isotope is what we call as the parent isotope. On the other hand, the stable isotope produced by radioactive decay of the parent isotope is the daughter isotope.
We're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today, but not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation.
Because radioactive decay occurs at a steady rate, scientists can use the relative amounts of stable and unstable isotopes present in an object to determine the object's age. Remember, the rate of radioactive decay is constant, so scientists can compare the amount of parent material with the amount of daughter material to date the rocks. The more daughter material there is, the older the rock. If you know the rate of decay of a radioactive element in a rock, you can figure out the absolute age of the rock. Half-life is the time needed for half of a sample of a radioactive substance to undergo radioactive decay. After every half-life, the amount of parent material decreased by 1/2. If you are going to take a look at this illustration, the red circles represent the parent isotope or parent material, while the blue circles represents the daughter material or daughter isotope. As you can see in the first picture, which depicts a rock that is formed in 0 years, you can see that all the radioactive substance present are parent materials or parent isotopes. This only means that there is no radioactive decay yet that is happening. On the second picture, after 10,000 years of that rock, you can see that half-life has happened, meaning we have half parent isotope and half daughter isotope. After 20,000 years in the third picture, you can see that 1/4 of the rock is composed of parent material and the rest is composed of daughter materials. And for the fourth and fifth pictures, the parent material or isotope is gradually decreasing. This only means that as time goes by, the parent material undergoes radioactive decay and only daughter materials or isotopes are left. This only concludes that the higher the daughter isotope or material present in a certain rock, the older the rock is. Scientists use different radiometric dating methods based on the estimated age of an object or a rock. And there are 4 radiometric dating techniques. The first one is Potassium-Argon method. Potassium has a half-life of 1.3 billion years, and it decays, leaving a daughter material of argon. This method is used mainly to date rocks older than 100,000 years old. Number 2, the uranium-lead method. Uranium is a radioactive isotope with a half-life of 4.5 billion years. Uranium decays in a series of steps into lead. The uranium-lead method can be used to date rocks more than 10 million years. The long half-life of uranium makes it possible to date only the oldest rocks. The third one, Rubidium-Strontium method. The unstable parent isotope rubidium forms a stable daughter isotope strontium. The half-life of rubidium is 49 billion years. This method is used for rocks older than 10 million years. For the last 3 radioactive dating techniques, those are all for rocks. For this one, we have for fossils as well. Carbon-14 method. carbon is normally found in three forms: the stable isotope carbon-12 and carbon-13, and the radioactive isotope carbon-14. Living plants and animals contain a constant ratio of carbon-14 to carbon-12. Once a plant or animal dies, no new carbon is taken in. Radiocarbon dating involves determining the age of an ancient fossil or a specimen by measuring its carbon-14 content. Green plants absorb the carbon dioxide, so the population of carbon-14 molecules is continually replenished until the plant dies. Carbon-14 is also passed on to animals that eat those plants. The amount of carbon-14 begins to decrease as the plant or animal decays. The half-life of carbon-14 is 5,730 years. The carbon-14 method of radiometric dating is used mainly for dating things that lived within the last 50,000 years. If you can take a look at this illustration, we have a rock that is newly formed, the same rock that sometime later has undergone changes, and the same rock at a later time. As you can see, the red dot represents uranium. In a newly formed rock, uranium is the only element present, the radioactive element present in that rock. But after some time later, you can see that there is also a presence of lead, which is almost the same with the number of uranium. And on the third picture, you can see that there is more lead than uranium. Thus, the older rock is, the larger the number of daughter elements or daughter isotopes, and the smaller number of parent materials or parent isotopes that are found in our rocks. I hope that we have reached our 3 goals for this week. I hope that you can now explain the movement of our plates leading to folding and faulting. Number 2, you should know now and describe how rock layers or rock stratification is being formed. And number 3, you need to know how to explain relative dating and absolute dating to define what is the age of a rock. That wraps up our discussion. I hope you learned something new today. Just always have the mindset that there is more fun in science. If you still have questions and clarifications, just write it down on your module or you can message your Earth and Life Science teacher. It has been a wonderful day of learning and discovery that even COVID-19 can never stop. See you again tomorrow, same time, from 12 noon to 12:30 p.m. here on DWND-FM, CMD Cablevision, and follow the FB page of SDO Kawayan for more live updates and information. Remember that education must continue amidst the crisis. This has been your teacher, Jaiseline Cornejo for BTV Eskwela, bringing education to your homes. Keep safe, everyone.